Hi, so I wanted to go over some quantum mechanics, and in talking to someone who is not familiar with quantum mechanics at all, it kind of inspired me to do a series of videos explaining quantum mechanics. Now, my goal would be to make videos to sort of make quantum mechanics more accessible to people who aren't so familiar with it. However, before I can get to that point, I think I'm going to just start with explaining quantum mechanics in the way that it was explained to me. And what I'm going to do is a series of videos where I will actually just go through the textbook by Griffiths, which if you are a undergraduate in physics, you're probably very familiar with Griffiths textbooks. So I'm going to just go over the quantum mechanics textbook by Griffiths, and just each video is going to be one section. So the first one is going to be Griffiths section 1.1, and this is about the Schrödinger equation. And just as a quick introduction about kind of my goals here to sort of demystify quantum mechanics. The reason why I'm starting with something more technical rather than starting with attempting to do quantum mechanics without, say, the math is there's a quote here that I'll read straight from Griffiths, which I really like, because one of the great things about this book is that he says, quote, "The purpose of this book is to teach you how to do quantum mechanics." And I think that's really important, and he goes on to explain, quote, "Apart from some essential background in Chapter 1, the deeper quasi-philosophical questions are saved for the end. I do not believe one can intelligently discuss what quantum mechanics means until one has a firm sense of what quantum mechanics does." Unquote. So what I really love about that is that um, I keep seeing things that are attempting to sort of justify somebody's crazy ideas or outright scams by using quantum mechanics as a justification. Either they know most people don't know quantum mechanics, or they themselves have misunderstood some really integral parts of quantum mechanics. So I think it's really important that you first understand what quantum mechanics does, because it's real and it's part of our world, and then we can get into what quantum mechanics means. And maybe that can, very quickly be a guide for you, that if you see something that is justified selling you a product on the basis of quantum mechanics, maybe you should consider, did they explain what it does? Because if they haven't explained what it does, they probably don't understand what it means to even say quantum mechanics. But now on to our first part, which is going to be very short, hence the long preface. This is Griffiths section 1.1, which is the Schrödinger equation. So this comes about from, in classical mechanics, if we want to describe, say, the motion of a particle, we would look at Newton's second law, which will be force equals the mass times the acceleration. And then we can rewrite this in terms of a perhaps more helpful differential equation, where if we have our position in dimension x is a function of time, then the slope of that, or the derivative of it, is going to be the velocity. We do the same thing again. So just very quickly, the slope is going to be, if we have x is in units of meters, the derivative is going to be meters per time. the derivative, which will give us meters per second. Our velocity is in meters per second. We take that per time, we're getting units of meters over seconds squared. And that is the acceleration, which is also a function of time. We can do the same idea if we look at the relationship between force and potential energy. So if we have a potential energy V as a function of time, we take the time derivative of our potential energy, and what we're going to get is our force. And it's going to have a negative sign there. Oops. There we go. And that's going to be negative force. So we can rewrite this force equals ma. We can rewrite that as, and I'm going to take partial derivatives because our force will also have a spatial component, and on the other side we also are going to have spatial components. So we can have our force equals m dx dt. And this is where quantum mechanics is going to differ slightly. So instead of using Newton's second law to define a motion of our particle, the idea is to use a wave equation. So the idea is that if a particle is behaving like a wave, which we know from the single slit and double slit experiments, then we should be able to make an equation that defines the motion of our particle that is a wave equation. So one way, so just quickly kind of looking that over, if we look at energy, and energy is going to be the sum of potential energy, which is V, plus kinetic energy, which is going to be 1/2 mv squared. So that's our energy. However, we can also write this in a couple other ways. We can use the idea that energy is an operator, and when energy is an operator, we have it equal I to the h bar del dt. And then another thing that we can write in terms of operators is our kinetic energy term, which is 1/2 mv squared. We can write that in a little bit more convenient way, which is if we add a mass on top and on bottom, then what we get here is we get a 1/2 momentum squared over m. And then we can use the operator notation of momentum, which is going to be negative I h bar, and assuming it's only in one spatial dimension, x, we have del x. Now we put these together, and what we're going to get so on one side we have our energy is IH bar ddt, and since this is an operator, we want to know what this is acting on, what's it's taking the derivative of. So we can just put in a function psi. And then we have momentum squared. So we get an h bar squared over 2m. And we get that minus sign because we had our negative I in there, or 1 over negative I. And we get the second derivative, because we did that twice, del x, and then that's acting on psi. And then we had our potential energy, and that's times psi. So this is our Schrödinger equation. The function that satisfies this equation, this psi, which is going to be a function of x and t, and since the time derivative is going to be equal, so our time derivative over here is going to be equal to the second derivative of the spatial dimension. So that makes this a wave. And this was inspired by writing an equation for matter that was the same as writing an equation for a light wave. And then when we look into solving the Schrödinger equation, of course, we will want to solve for this, which is our wave function. So you'd probably hear that a lot, even if you're not familiar with quantum mechanics, or if you're a beginner in quantum mechanics, or maybe you'll be taking quantum mechanics this fall semester and you want to kind of get ahead. So a wave function is the function that satisfies the Schrödinger equation, and the wave function is going to have all the information about the particle or the system that we want to study. So we can use things that we know about the wave function, like maybe we will know its position at x equals 0, or maybe we will know the amplitude of the wave at time equals 0, or maybe we'll know that say our psi is going at x goes to infinity will equal 0. And we can use all of those boundary conditions to help us to solve this Schrödinger equation. So that's it for part 1.1 of Griffiths, the Schrödinger equation. This guy right here.